Hello class, we're about to start section 4.5, modeling with exponential functions. Note, any process that involves a repeated multiplier can be modeled exactly with an exponential function of the form f of x is equal to a times b to the x. This includes many important applications such as compound interest, population growth, level of medication in the bloodstream, radioactive decay, and much more. Now we come to example 1. It says a $10,000 deposit was made into an account that pays 4% interest, compounded annually. Let M of t represent the amount of money in the account after t years. Now let's look here at A. It says, fill in a table of values for the amount of money in the account. Use this to find a model for M of t by hand. Now, of course, I put in the table here that's already pre-filled because when I was trying to fill in the numbers, my numbers would jump. So just to make this a little easier, I had already included this table here. Now, we look here. We start off with t years. Your first year, which would be 0, would be the $10,000 you deposited. Now, you know, when you deposit $10,000, they're not going to give you the interest right then and there, especially since it said it's compounded annually. So after the first year, then your interest would be $10,400 because remember, your interest is compounded at 4% interest. So if you look here, we had $10,400. Now, if you look, we have our original $10,000, which is here. And after our first year, we add $400 more onto it. So what we have here is 1.04, or after the first year, you have 104% of what you initially put in. Think about it. You get your $10,000 back, which is 100%. And then you have an additional 4%, which written as a decimal is 1.04. So now to go from this first year to the second year, that's going to be another 1.04. So you will keep multiplying by this here. So we have 1.04 from the 0 year to the first year, from the first year to the second year, and from the second year to the third year. So now, let's take a look at this. Since we have our 4%, first of all, 10,000 is our initial investment. So we know that is our y-intercept. And we know this is our A, the 10,000. Now, for our B, which is in this problem here, we know it's the 4%, but remember, we also have to include the initial amount we had. So it'll be B, which is your base, is equal to 1.04. So our A is 10,000 and our B is 1.04 because you still will have your initial 10,000. So we will have M of t is equal to AB to the t, as we would substitute in the x that we usually would have with AB to the x, we'll substitute that in for t. So we have M of t is equal to, now our A is 10,000, and our B, which is our base, is 1.04. to the t power. And this is the equation that we have. Now we figured out the equation. Let's go down and look at B and C. It says, what is A in the model? We know that that is 10,000. It says, what does it represent in this situation? So we think about it. What does that 10,000 represent? It actually represents the starting amount. It's the starting amount in the account Again, it's the starting amount in the account, which is $10,000. It's the starting amount in the account, which is $10,000. Now it says, what is B in this model? We know that's 1.04 because that's our base, our multiplier. What does it represent in this situation? It represents every year the account grows by 4%. Now remember, even though our base is 1.04, remember your interest is the 4%. You just have to include 1.04 because after a year you add the interest and the initial principal. So now we come down here to D. It says how much money will be in the account after 15 years. So you'll substitute in 15 for T. M of 15 is equal to 10,000 times 1.04. And we know that will be taken to the 15th power, which gives us approximately $18,009.44, which you could easily punch into your calculator. Now on to the next page. It says here, note, in the next exponential model, f of x is equal to ab to the x. A represents the starting value of the dependent variable when x equals 0, or you could say the y-intercept. B represents the rate of change. Convert the value of b to a percent, then subtract 100%. This gives the percent rate of change of the dependent variable per unit rate of change in the independent variable. Just to explain this, remember our b was 1.04. Now 1.04 written as a percent is 104%. Now what they're telling you is when you have this percentage, subtract 100% from it. And then this will give you the percent that the account is growing or decreasing by. Okay, now half-life. The time required for something to fall to half its starting value. This is particularly useful with radioactive decay, physics and chemistry, as well as drug dosage and particulate absorption, nursing, allied health, biology. Those are some of the fields. Now we come here to example 2. It says the half-life of acetaminophen, the active ingredient in Tylenol, for example, is 2.5 hours. This means that if a person takes a medication containing acetaminophen, the amount of acetaminophen still in the body is cut in half every 2.5 hours. Working by hand, find a mathematical model given the amount of acetaminophen A in the body of a person T hours after taking the typical adult dose of 500 milligrams. Now, what we have here, we have this model already set up because, again, this had the number shifting. So what I did was I just put the completed model here. Now, what we have here is we have T, which goes by the hour. So we'll have the starting time, which is 0, and then we'll go by 2.5 hour intervals. Now, what we have is this here. We have A of T, which is 500. And at 2.5 hours, we end up with 250. But let's go over here and solve for this here. Now, we know A of T is equal to A times B to the T. Now, we have A of T. We have our A, which is our starting point, which is 500, times B to the T. Now, what we need to do next is this here. We need to, now again, in solving for B, we have to take into account what we have here in the problem. It tells us that the amount of this element will be cut in half every 2.5 hours. So let's go here. Our time will go from 0 to 2.5 hours. And we're already told that the amount in the body will be cut in half, which would be 250. So we have our T and our A of T. So our A of T would be 250. Remember, we're solving for B, is equal to 500 times B to the 2.5 power. Now, if you put this in your calculator, you would end up, well, first of all, let's divide each side by 500. So 250 divided by 500 is 1/2, and it equals B to the 2.5 power. Now, all we have to do is take the square root or the 2.5 root of both sides. 2.5 will be our root, and these will simplify out. The 2.5 root of 1/2 will give us B is approximately 0.7578. We're around the 4 decimal places. So, okay, class, I said the final answer was B. It's approximately 0.7578. It actually should be 0.7579, not 78. That was a slight error. Okay, now, another thing. If you notice, when we look at this model here, you notice that this is going down by half. So you may ask yourself, why isn't B 0.5? The reason being is this here. If you notice, we're not going by every hour. Remember, with this exponential notation here, or this exponential function, which we have here, the exponential model, remember, our t or our x value must go in multiples of 1, in intervals of 1, and we don't have that. So this b is approximately 0.7579, is assuming that this is going in intervals of 1. So now, we will have our model here. We will have A of t is equal to our basis, our A is 500. Our base is approximately 0.7579. And remember, that's taken to the t power. So this is our equation. Now, it says, what is A in the model? Now, we know A is 500. And what does it mean? The starting amount of the acetaminophen was 500 milligrams. Now see, it says what is B in the model? We know it's 0.7579. And what does this mean in this situation? Now remember, we have to do this. We have to take our B, which is 75.79%, and subtract 100% from it, which we got earlier when we first got to this page here. 75.79 minus 100% will give a negative 24.21%. That means every hour, the amount goes down by 24.21%. Now we look at D.